Okay, good afternoon. My name is Rantzer. I'm a control theorist from Lund University. Actually, the main author of this paper is Bin Hu. He is at the University of Wisconsin. Unfortunately, due to visa reasons, he could not be here. But it's really a collaborative work where we are using control theoretic methods for analyzing dynamical systems to analyze the convergence of stochastic optimization methods. So this is my outline. I'd like to first introduce some theory to analyze what we call jump dynamic systems. And then I will show you how stochastic optimization algorithms fit into this framework. And this allows us first to do numerical computation of rate bounds for stochastic algorithms, but also to do analytical rate bounds. So a jump linear system is something of the following form. Here you update the state psi at every time step using the matrices A and B, where W is some external input. And the pair A and B is selected randomly from a set of pairs that is given. So this is a linear system which models the algorithm. But then there is nonlinear feedback. So this linear system now is fed with inputs that are computed in a nonlinear fashion from the previous state. So altogether this becomes a nonlinear jump system. So of course we need some assumptions about the nonlinear part, and these assumptions are given in terms of quadratic inequalities. So it's assumed that the delta is a map from psi to W that has the property that this quadratic inequality always holds. And in the simplest case, it would hold for all possible input pairs, but actually in more generality, we only require that it holds when you integrate over time and the W and psi are solutions to such a linear equation. Anyway, if we combine the linear equation with the quadratic inequalities, we can prove a convergence rate which is now given as expected values, and see that they must converge geometrically. And this parameter rho is something we can compute by solving a semi-definite program. So the statement is that if given the A and B matrices and given the quadratic inequality specified by M, if we can solve this linear matrix inequality for a positive definite matrix P and some non-negative variables lambda for some specified rho, then we have proved the convergence rate of rho. So that's the theorem, and actually it's rather trivial to prove it, because if you notice here that you multiply M from right and left by this vector, if you do that same thing with this expression, you see all these terms become non-negative, so the only chance that the total becomes negative is that the first term is negative. And this becomes a telescope sum when you apply the linear inequality. So everything but the first and last expression vanishes, and all that remains is this. Okay, so that's the theorem. Now we're going to apply this to stochastic optimization algorithms. And there is a large family of such optimization algorithms that fit into this context. This is just one example. We want to minimize an expression like that, and we want to select at randomly one index and compute the corresponding gradient. So this is done at every time instant. We compute a gradient for a randomly chosen f, and then we keep in the memory all those computations we have done before. And from this, we compute an estimate of the gradient, and we apply a gradient step. So all of these methods now fit into this context of a dynamic jump system. So we have a linear part, which is random, and a non-linear part, which is the computation of gradient. And at every time step, actually, it's only one of these that is used, and that is due to the sparsity of B. So for all of these different methods that are well studied in the literature, you have corresponding matrices A, B, and C, actually, which goes into this matrix M. The sparsity is, of course, essential. And then the quadratic inequalities, they come from assumptions on our objective functions. So if you have L smoothness and M strong convexity, you get the quadratic inequality that is satisfied by the gradient. And here I'd like to emphasize that you can have different quadratic inequalities for the sum G and for the individual terms Fi. So you can have a convex sum, but individual terms need not be convex, for example. So when you now, in order to solve this semi-definite program, you exploit, of course, the sparsity of the matrices, and that allows you to reduce significantly the complexity and the number of parameters in the semi-definite program. So for example, here we have just 2 parameters to optimize. And if we see what this gives us in the special case of the Saga algorithm, we get 2 linear matrix inequalities corresponding to the assumptions on G and F. And we get a rate bound which looks like this. In this case, we have not only solved it numerically, but analytically guessed values of these parameters. And it turns out that in very many cases, what you do is to first solve numerically, and then that allows you to guess something analytically. So let me summarize by saying this is a unified method. It allows us to make more or less automatic rate analysis for stochastic optimization methods. In the first step, you can use numerical algorithms to search for convergence rate, and then if you find solutions numerically, you can go on and try to make analytical proofs by symbolically solving the semi-definite program. And it allows us also to explain why some methods like SAG are more difficult than SAGA, because they require the use of more complex quadratic inequalities, essentially. There is much more to say about that, but my time is running out. So thank you very much for your attention.
Questions? While the next speaker sets up, go ahead.
Just a basic question. Can you perhaps recall what the systems are aimed at modeling?
Yeah, the question was, what are these systems aimed at modeling? Of course, jump linear systems can be used to model many things. In this case, they are aimed at modeling what happens when you connect an algorithm to an oracle that generates gradient values. That's the feedback loop.
Any other questions? Okay, let's thank Anders again.